Welcome everyone to the first webinar of 2015 here at VisualSonics. My name is Meena Lakshman and I'm the Scientific Applications Marketing Manager here, and we'll be moderating this webinar. The webinars for this year will pay tribute to all scientists bringing discoveries to patients. This is the theme for 2015, and this webinar platform, particularly thereby, is available to you to voice or share innovative thinking to the challenge of understanding diseases and developing therapies. Our speaker today is no exception to this thinking. In fact, I'd like to share his biography at this particular time. Mathew Platt is a senior PhD candidate in the laboratory of Dr. Jeremy Simpson and in the Department of Human Health and Nutritional Sciences at the University of Guelph. Mathew's interest in cardiovascular research stems from his projects prior to MSc and now has successfully become his doctoral thesis. Under the expert mentorship of Dr. Simpson, Mathew has gained experience in developing and investigating animal models of cardiac dysfunction. His current research is on cardiac remodeling following a heart attack. He is a recipient of numerous awards as listed out here. Just before I go over to his presentation, if I can get the slide prior to this, I would like to make some housekeeping notes. For all of you at this webinar, a recording of the webinar will be made available. If you have registered and no friends that have registered and could not attend the webinar, a recording will be made available. All lines will be muted for the duration of the webinar. Please use the chat window on the lower right of your WebEx screen for questions. We will have a question period at the very end of the webinar. We expect the webinar to go over 45 minutes, and we will have a 5-minute announcement at the very end. All right. Our speaker today, his presentation will educate us on a new method to measure cardiac output in an MI model. As we move to his first slide of his presentation, we will switch the privileges to Mathew Platt.
Hi everyone, as I was just previously introduced, my name is Mathew Platt and I'm a PhD candidate in Dr. Jeremy Simpson's cardiorespiratory lab at the University of Guelph in Ontario, Canada. And today I'm going to present to you on pulmonary flow as an improved non-invasive method for evaluating post-myocardial infarction cardiac output in a murine model. So first I'm going to go into a little bit of an outline as to what I will be presenting today in the webinar. First, what is pulmonary flow and why exactly pulmonary flow is useful? Next, I will explain my method on how I calculated pulmonary flow. And then I will go into left ventricular echocardiography and the classic means of measuring cardiac volumes and the assumptions that are integral to correct cardiac volume assessments. And finally, I will explain the remodeling phase post-myocardial infarction and how pulmonary flow actually acts as an improved method for accurately determining cardiac output in these mice. So first off, what is pulmonary flow exactly? And pulmonary flow is the blood flow through the pulmonary trunk. The pulmonary trunk is the greater vessel exiting the right ventricle, shown here in blue. And pulmonary flow is the flow acquired just before the pulmonary artery bifurcation to make sure you're getting the complete volume of blood and not a partial volume of blood. This is located right beside or underneath the aortic arch. So stroke volume can be calculated using Doppler principles. And what Doppler principles are is they use sound waves that are shot in the direction of blood flow. And the sound waves, when they come back and are reflected towards the transducer, will pick up the velocity and the direction of blood flow. Cardiac output can be calculated, obviously, using the formula stroke volume multiplied by the heart rate. So to explain in a little bit more detail how the Doppler principles work, using the new Vivo 2100 machine, we had the privilege of using color Doppler. Now, color Doppler will actually colorize the Doppler image so you can figure out the direction of blood flow. If the transducer is emitting sound, and that emitting sound comes back in a red color, it is because the blood flow is moving towards the probe, and blood flow moving towards the probe will actually increase the speed of the reflected sound waves. Now, in the exact opposite direction, if the blood flow is moving away from the probe, this will actually absorb some of the energy from the sound waves, and the reflected waves will be slowed down, showing up blue. The colorization of the Doppler allows you to visualize very quickly the direction of blood flow, and this helps to identify the vessels that you're looking at. So another thing that is integral to the usage of color Doppler, or Doppler in general, is the Doppler angle. The Doppler angle is the angle of acquisition between the emitted sound waves and the direction of blood flow, and it is integral that this angle remains below 70 degrees. Any Doppler angle above 70 degrees will start to increase the percent flow error, and if you increase the percent flow error, this decreases the accuracy of acquired volume calculations. This is because as you increase this angle, you are now starting to shoot sound waves perpendicular to blood flow, and the Doppler principle is dependent on the reflection of blood flow either at an increased or a decreased speed. So to give you an example of why I chose pulmonary blood flow specifically, it's because the pulmonary trunk is ideally situated for the ease of Doppler acquisition. This here is an image taken from the pulmonary trunk of a mouse. As you can see, the color Doppler shows up blue because the blood is being ejected from the right ventricle down and away from the probe. The red arrow represents the direction of blood flow, and the white line represents the pulmonary trunk diameter at the point of acquisition. As you can clearly see here, the angle of acquisition is well below the 70-degree cutoff. This dotted line here represents the direction of blood flow, which is pre-selected by the user. This direction of blood flow needs to be parallel to the lines on either side representing the pulmonary trunk walls. Conveniently, in the study that I undertook, theta, or the angle of acquisition, was well below 60 degrees in all 56 mice used in this study, which increased the accuracy of the acquired volumes that I calculated. So what exactly is pulmonary flow? There is one method that the new Vivo 2100 and the Vivo 3100 machines allow you to do, which is called steering the beam. So in the instances where you may have genetic models or genetic abnormalities and your theta, say you have anatomical variations where your vessel is no longer located in an area that allows you to have a low angle of acquisition, you can actually steer the sound beams coming out of the transducer to reduce your Doppler angle. Conveniently, as I mentioned previously, we didn't need to use this technique because the pulmonary trunk was easily situated and the Doppler angle was always well below 60 degrees in this study. So why specifically pulmonary flow? This is because the pulmonary trunk was much easier to image than the aorta. Unfortunately, the view of the aorta is often more obstructed, so this here represents the angle or the probe position to acquire the aortic arch or the ascending aorta. It's the suprasternal notch view. In humans or other large mammals, there is a lot of tissue at the top of the sternum that allows for probe placement to accurately obtain a clear image of the aorta. Unfortunately, in mice, there is a much smaller window of acquisition, and sometimes you'll get the ascending aorta placed right behind the sternum, and you're not able to visualize the aorta as clearly. At the same time, there's also more turbulent flow in the aorta, especially in surgical models such as transverse aortic constriction. When you have a constriction, you actually take laminar blood flow and turn it into turbulent blood flow. And as I previously mentioned with the Doppler principles, it's dependent on the direction of blood flow to accurately determine blood velocities. When you have turbulent blood flow, the change in direction skews the measurements and provides incorrect volume calculations. This is highlighted by results from my study, where the pulmonary trunk was easily situated for ease of image acquisition in every single mouse that I used for this study. Unfortunately, the aorta was only visualized 13 of 15 times in healthy mice, 4 of 13 times in a transverse aortic constriction model, and 15 of 28 times in a myocardial infarction model. Excluded images were images where the vessel walls were not clearly delineated, or in sequential image acquisitions, the volume measurements, as done at a later date, varied by more than 10%. Now, we are not the first lab to use pulmonary blood flow as a surrogate to calculate cardiac output. Tourneau and his colleagues in 2011 compared pulmonary blood flow, two-dimensional left ventricle cardiac volumes, and the more commonly used M-mode volume calculations from the left ventricle, all against a flow probe, and found that pulmonary blood flow, just the same as 2D and M mode, was equally reliable in calculating cardiac volumes and was actually associated with the least amount of variability between measurements. Now, they chose pulmonary blood flow over aortic flow for the exact same reasons that I previously mentioned: the ease of acquisition and the low variability in repeated measurements. So before I go into some of my data comparing pulmonary flow and the other methods of calculating cardiac volumes, I want to emphasize that pulmonary and aortic flow are interchangeable. So these are 13 mice where I was able to obtain both pulmonary flow and aortic flow repeatedly. The dotted line represents the line of identity, or the slope of 1, and in all 13 mice, they very closely approximated opposing flows. Aortic flow and pulmonary flow both equaled each other. This is based on the assumption that the left and right ventricles pump blood equally and pump equal volumes of blood. Again, this emphasizes that I chose pulmonary flow over aortic flow because of the ease of acquisition of the images. Now, we found that pulmonary flow consistently correlated with both M mode and with 2D derived cardiac outputs. Each individual point represents one mouse, the black points representing healthy mice, and the red points representing transverse aortic constriction mice, which is a model of heart failure. And you can see that both at high absolute values and low absolute values, the relationship held true, and pulmonary flow adequately correlated to the left ventricle derived cardiac volumes. All these images were acquired within 5 minutes of each other at similar body temperatures and heart rates to reduce the variability in calculated cardiac outputs. Now, before I get into it later, I will be explaining why pulmonary flow is an improved method to calculate cardiac outputs, specifically in mice post-myocardial infarction. But before I get to that, I want to explain some of the benefits behind pulmonary flow. So as I mentioned previously, there is a low intra- and inter-operator variability, as was previously described by Tourneau in 2011. And especially, it's not dependent on images acquired from the left ventricle. This is especially valuable on hard-to-image left ventricles. So for example, this is a B-mode short-axis image from the left ventricle, where the left ventricle is right here on the right side of the image. The yellow line is an M-mode location, and here is your resulting M-mode image. As you can see, the top wall is clearly delineated, but the bottom wall is kind of mucked up. And this happens sometimes due to, again, anatomical variations or possibly a location of the left ventricle behind the septum that makes it very difficult to image. In these cases, pulmonary flow provides an accurate surrogate to calculate cardiac output when cardiac output cannot be properly calculated from the chamber dimensions. This is also valuable in expensive animals or in rare genetic models where information from an individual animal is integral to the success of the study. If you only have an N of 4, a secondary method to validate cardiac output is incredibly valuable for that study's success. So now that I've explained some of the benefits of pulmonary flow, actually I have one more. Because pulmonary flow validates stroke volumes, it's especially useful for subsequent measurements such as a pressure volume loop analysis. As you can see here with the SciSense device that our lab uses to evaluate pressure volume loops, that they are dependent on the manual input of a stroke volume. In the case where the left ventricle is hard to image, stroke volumes can be hard to accurately determine. Pulmonary blood flow allows for a more accurate measurement of stroke volume to confirm the inputted value so that the subsequent measurements are more accurate. So now that I've explained some of the benefits of pulmonary flow, I'd like to go into the method that I use to calculate pulmonary flow and how simple it is. So the orientation of the probe is very similar to the parasternal long axis placement used to classically image the left ventricle. Here you can see a mouse on the VisualSonics table with the probe, the M5 or the MS550D probe, placed parasternally right along the left ventricle. That's to acquire the classic B-mode image. Now, to acquire pulmonary flow, all I do is rotate the probe about 1 centimeter superior underneath the chin, as you can see by the probe moving slightly past this line. The orientation of the probe, I'd like to first actually go into how you orientate the plate so the animal is properly placed on the platform, so the probe can be properly placed on the animal. You're going to want to tilt this plate down, and you're going to tilt it to the animal's right. That is seen here as you tilt the plate down and then tilt the animal over to the right. Now what this is going to do is going to move the sternum out of the way of the probe, so when the mouse is placed on the table, you can clearly visualize the greater vessels behind the sternum. So now I would like to use a video to demonstrate exactly how easy. Now I'd like to use a video to demonstrate exactly how easy pulmonary flow acquisition can be. Okay, here now we have our classical image of the left ventricle as I hit play. I've activated color Doppler, which is why you see the colors. Now all I'm going to do is rotate the probe 1.5 to 1 centimeter superior, and you'll see starting up here in the top part of the picture, the blue is actually the pulmonary trunk as the blood is ejected from the right ventricle out and down through the pulmonary trunk. So I'll play that one more time. We have a classical image of the left ventricle, and all I will do is rotate the probe 1 centimeter superior, and you will see in the top part of the image the blue representing the blood flow coming out and away from the probe, and that there is the pulmonary trunk. Now this holds true in disease models as well. And my second image here, or my second video here, is of a mouse post-myocardial infarction. So you see the left ventricle is slightly different. Instead of a normal contracting myocardium, you'll have thin akinetic tissue around the outside. The only part of the contracting tissue is on the bottom of the image. Again, as I rotate superior, you'll see very clearly coming into view the blue color Doppler representing the blood flow coming out of the right ventricle down through the pulmonary trunk.
Matthew, could you show exactly where the pulmonary trunk is?
Unfortunately, the cursor will not allow me to highlight.
Okay. All right.
I can play the image one more time. Unfortunately, the cursor is not allowing me to highlight the movie. You'll see in the top right part of the image an empty square or an empty area. As the blue shows up, that there represents the pulmonary trunk. This is why color Doppler is so valuable, because the color represents the direction of the blood flow and allows you to easily visualize the pulmonary trunk. So more onto the method. How exactly do I calculate stroke volume? So stroke volume from flow is a product of the velocity time integral multiplied by your pulmonary trunk area, or the area where you are locating your the velocity. So I will go back to this image here where I have the white line representing the pulmonary trunk diameter, and again the red arrow representing the direction of flow, with blue representing the blood flow down and away from the probe. This here on the right represents a Doppler tracing of the blood flow for each contraction, with the y-axis being the velocity in millimeters per second and the x-axis being time. The velocity time integral is merely the area under the red line and can be calculated from the right ventricular section on the Vivo 2100 pull-down menu. So once you've calculated the velocity time integral, you also need to calculate the pulmonary trunk area, and it is integral to this measurement that you take the area from the exact same point where you were taking the velocity. To do this, you will merely take a zoomed-in B mode of the pulmonary trunk, and the way that I did it was you average 3 separate contractions and make sure that you're taking the pulmonary trunk area in diastole, because that is when there is the least amount of variability in pulmonary trunk diameter. So finally, I will go through quickly how to calculate cardiac output from the VTI. So as mentioned previously, cardiac output is the product of stroke volume and heart rate, and the stroke volume can be calculated using the velocity time integral multiplied by the pulmonary trunk area. Pulmonary trunk area is a product of pi times the pulmonary trunk radius squared. And that'll get you the surface area at the point where you are taking the velocity time integral. If you break this down into units, we are getting millimeters per beat, which is the velocity time integral, multiplied by millimeters squared over beats per minute. And if we break this down, it becomes millimeters cubed per minute, which is otherwise a volume measurement in microliters per minute. You could easily divide this by 1,000 to get the more commonly used milliliters per minute to calculate cardiac output in mice. So pulmonary flow is obviously not the only way to calculate cardiac volume. In fact, there are multiple methods, such as thermodilution, pulse pressure, flow probe, MRI, especially MRI being the gold standard. But unfortunately, a lot of these other methods are either invasive in the way of thermodilution, impractical in rodent models, such as pulse pressure, or very expensive. MRI machines run upwards of $1 million and require very specific technicians to both operate and repair. Unfortunately, most labs don't have access to this equipment or the funds to purchase one. And as such, echocardiography remains the gold standard for comparative evaluations of cardiac output in both mice and men. Echocardiography is even more valuable because it's non-invasive, which allows you to use repeated measurements over time. It's specifically built for rodent models in the case of the Vivo machines. It produces very high resolution images and is a low comparative cost when you're comparing it to something like an MRI. So now I'd like to go through some of the basics of echo and how volumes are calculated. So volumes are generally calculated from the left ventricle using chamber dimensions. These are 2 of the most common used methods. The 2-dimensional method, which relies on the input of 2 individual variables, A being the left ventricular longitudinal area, and L being the left ventricular longitudinal length. And this formula here can be used to calculate the volume of that 3-dimensional shape. There is also the more commonly used M mode, or one-dimensional, and it's one-dimensional because there's only the input of 1 variable, that being the mid-papillary left ventricular diameter. And this uses the modified Tykof's formula to calculate volumes. So this is an example of what images acquired would look like in vivo. Here at the top, we have the 2D images, which requires a longitudinal section of the left ventricle. Here we have the area in diastole and the length in diastole. And over here we have the heart in contracted form, which is in systole, and we have the area in systole and the length in systole. And using the formulas that I described previously, you can calculate stroke volume as the difference between the diastolic volume and the systolic volume. This is the ejected volume. Here's an image of a left ventricle using M mode, which provides one-dimensional measurements, and you can use the end diastolic dimension, which is the widest dimension, against the end systolic dimension. And again, using Tykof's equation, you can calculate the difference in volumes between diastole and systole, and in the end, the stroke volume. So for simplicity's sake, I'm going to specifically focus on the one-dimensional M-mode images and some of the assumptions that are integral to a properly calculated cardiac volume. So again, here's the formula, where the only inputted variable is D, or the mid-papillary left ventricular diameter. And here we have an artistic representation of the left ventricle, both in diastole and in systole. Again, stroke volume is the difference between the diastolic volume, as shown here, minus the systolic volume, obviously in 3 dimensions. Some of the assumptions that are integral to the success of this formula are, 1, that the left ventricle maintains an ellipsoid shape, as depicted up here in this image, that the wall kinetics are uniform, meaning that the wall contracts uniformly, as depicted down here, roughly even contraction between all the walls, and that the wall composition and thickness are uniform, that the wall is composed of healthy, normal kinetic myocardial tissue, and that at all points the wall thickness is relatively the same. This means that the mid-papillary wall dimensions and the wall thickness are representative of the rest of the heart. These assumptions were described by Tykov back in 1976. Now I'd like to show you another video. This is again a short axis view of the left ventricle, just to describe how the left ventricle maintains these assumptions in a healthy heart. So as you'll see here, we have normal kinetic tissue all the way around the heart. At the same time, the wall thickness in diastole is relatively uniform, and the wall composition is uniform, as we can tell by the fact that the left ventricle is contracting normally and has even thickness throughout. Now, following a myocardial infarction, again, this being an artistic representation, there's certain remodeling phases that skew some of these assumptions. Here we have the healthy myocardial tissue remaining in pink, akinetic scar tissue represented by blue, and there's also hypokinetic tissue where there's a mix of fibrotic fingers as well as healthy contractile myocardial tissue left over. So when you have a myocardial infarction, you get a dilated chamber. This chamber is now much larger than the chamber was originally. This leads to a distorted balloon-like shape, which is more oval or circular and no longer ellipsoid, as well as there is now a non-uniform left ventricle wall composition and wall kinetics. Some of the wall is made up of scar, some of it made up of a mix of fibrosis and healthy tissue, and some of it healthy myocardial tissue. So again, I'd like to use a video to describe this. As I hit play, you will see in the bottom right, there is healthy contractile tissue, whereas in the middle, there is tissue that's remaining, but is hypokinetic in comparison to the tissue to the right of it. All the way around the outside, we have thin akinetic scar tissue, which is no longer contracting. And as is clearly indicated by the difference in wall thickness, we no longer have the same wall composition. This means that my mid-papillary wall diameter at that D point, my mid-papillary wall diameter is no longer representative of the global cardiac condition. So what this means is there's actually an increased error or an increased potential for human error when looking at the heart post-myocardial infarction. So here what I've done is I've taken a healthy animal, a healthy heart, a heart subject to 18 weeks of transverse aortic constriction, and a heart following 18 weeks of myocardial infarction, or 18 weeks post-ischemic injury. The white line in the middle represents the mid-papillary wall dimensions, whereas the dotted lines on either side represent the possible variability of 0.5 millimeters in either direction on either side of that mid-papillary point. So what I did is I calculated the end diastolic and the end systolic dimensions at these different points, and found that in both the healthy and the TAC mice, the difference in diastolic and systolic dimensions was well below 5%. whereas in the myocardial infarction heart, the difference in diastolic and systolic dimensions was 15 and 20% respectively. This translates to a massive difference in stroke volume and calculated cardiac output, the stroke volume being over 100% different between the leftmost line and the rightmost line, and the cardiac output being as low as 4.9 milliliters per minute on the left, from the left line, and as high as 20 mils per minute from the right line. This is owing to a difficulty in landmarking the papillary muscles following a myocardial infarction, as specifically in mouse models, you can get heart attacks that consume upwards of 60 or even 70% of the left ventricle, and in some cases can completely ablate the landmarks that are generally used to place this mid-papillary wall diameter line. So why pulmonary flow? Now I'm going to bring you back to the image that I used initially, where I correlated pulmonary flow to left ventricle M-mode derived cardiac output. And remember, I showed that in both healthy and in a model of left ventricular dysfunction, there was a strong correlation between both pulmonary flow derived cardiac output and left ventricle derived cardiac output. Now, the divergence that I noticed in the MI mouse hearts is likely due to excessive left ventricle remodeling, which skews the classical assumptions that are used to calculate cardiac output from the left ventricle. What I'd like to bring your attention to is specifically the range of cardiac outputs. There is a much tighter range of cardiac outputs from pulmonary flow, ranging between 30 and just below 20 mils per minute in all 28 mice evaluated. Whereas in the left ventricle, the range was between about 5 and 25 mils per minute. Now, between 4 and 18 weeks post-myocardial infarction, we have a very low mortality in our mice, which is more consistent with the range of cardiac outputs following pulmonary or from pulmonary flow. In fact, if we look at these mice on the left here, based on their left ventricle, they have cardiac outputs that are below 10 mils per minute. In that case, they are well below 30% of what their original cardiac output values would be, which would indicate that we would have a much higher mortality than we are noticing between 4 and 18 weeks, indicating pulmonary flow is likely a much more accurate method of grading the absolute cardiac outputs following a myocardial infarction. So what are some of the implications of this? Well, as I've mentioned, pulmonary flow is unbiased to the anatomical changes or remodeling that occurs in the left ventricle. Pulmonary flow has low intra and inter-operator variability, which allows repeated measurements from different individuals to have less variability between them. This reduces the potential for human error and increases the significance of study findings. So it'll also improve the accuracy of your study conclusions. Furthermore, by reducing data variability, this permits for reduced N values. If you have a very small difference between two groups of animals, the reduced N value or the reduced variability will allow you to tease out the slight differences in cardiac outputs much easier and much quicker. This is especially beneficial when we're talking about describing a brand new genetic model where cardiac function is unknown, or following a pharmaceutical intervention where we may be looking for very small or very slight changes in cardiac function. So without being redundant, to give a slight recap of what I've gone over, pulmonary flow is an improved method to evaluate cardiac output following a myocardial infarction. It consistently approximates the left ventricle-derived volumes in healthy mouse hearts as well as in mouse hearts post-transverse aortic constriction. It is very easy to obtain, as I demonstrated with my videos, where you can take an image of the left ventricle, simply shift that image up about 1 centimeter and get a clear view of the pulmonary trunk. And there is low internal variability, as was also indicated by Tourneau and his colleagues in 2011. It is unbiased to the anatomical changes or remodeling that occurs in the left ventricle following the myocardial infarction, and it has an improved accuracy of volume calculations following an MI. This is beneficial if you're going to be doing pressure volume loops where you want an accurate stroke volume before you use the subsequent measurement. So this manuscript is entitled Pulmonary Flow as an Improved Method for Determining Cardiac Output in Mice Following Myocardial Infarction, and it's currently submitted with myself as the primary author and Drs. Keith Brunt and Jeremy Simpson as co-senior authors. So this brings to a conclusion my webinar on pulmonary flow and its benefits following myocardial infarction. I'd like to give specific acknowledgments to the University of Guelph, as well as my department, the Human Health and Nutritional Sciences Department, and Drs. Jeremy Simpson, Drs. Keith Brunt, and Meena Lakshman. Jeremy and Keith being both co-authors, as well as on my PhD committee, and Dr. Meena Lakshman as the VisualSonics correspondent that made this all possible. If anybody is interested in receiving an update on the status of our manuscript or possibly a version ahead of print, please just feel free to contact me either at plattm@uofguelph.ca or by visiting our lab website at simpsonlab.weebly.com. Thank you very much.
All right, Matthew, I guess I have to say a lot more favorable words to you. That's very kind of you. A really good presentation. We are now at 20 minutes to closing the presentation. This is time for questions. We have a couple of questions coming through. Please continue to put your questions. This is the time for us to learn and engage. Some of the questions that we have here, Matthew, if you don't mind actually commenting on the models that you did and the measurements that you are proposing here as a new method for cardiac output. How was your EF and basically ejection fraction and fractional shortening for MI models, particularly the ones that you talked about here?
EF and FS were classically calculated from the left ventricle. Unfortunately, with fractional shortening dependent completely on the diastolic and systolic dimensions from the left ventricle, there was no way to improve that method of calculation. However, there was a slight improvement on the calculation of ejection fraction, as stroke volume is correctable using pulmonary flow. It is just the end diastolic volume, which is still completely dependent on left ventricular dimensions. And as such, ejection fraction was only about 50% corrected. When it comes to other measurements from the left ventricle, yeah, that's about it.
Okay, all right, thanks. I think along those lines, there is the aortic outflow method. Do you have any comparison? Was that shown in your study, comparison with aortic outflow method?
No, although the aortic outflow method is valuable and does provide reproducible results, we found that in too many of our surgically altered mice, the image of the aorta was less consistent as the image from the pulmonary trunk. So although valuable in a subset of mice, it wasn't as valuable as pulmonary flow was in every single one of our mice. And this is just due to the angle of acquisition and the ease with which the pulmonary trunk is visualized.
All right, I think that's a very important point that, when you and I talked about your work, is when do you use this pulmonary flow method? When do we use this new method for cardiac output measurements? It is when there are such changes, imaging issues. This is an MI model, and the ability to see certain imaging anatomies will drive whether you use this method over other methods like aortic flow.
Yeah, exactly. Well, pulmonary flow is specifically valuable anytime that you have any sort of alterations to the left ventricle when you don't have the ability to do three-dimensional analyses. Mm-hmm. Obviously, an MRI would be the gold standard because you can get a complete three-dimensional analysis of the left ventricle both in diastole and in systole. However, in the absence of that, the flow through the pulmonary trunk provides a less biased method that is acquiring blood volumes without being dependent on those anatomical changes.
And also, one has to keep in mind that these kinds of calculations you are making in real time, and physiology does get affected by the heart if due to isoflurane or anesthesia. So you want to acquire these images very quickly, and ultrasound does have value to it, and thereby a gold standard in most echo-related studies. How do you control your MI model heart rate? I think we talked about this as well for these models.
Heart rate was controlled by the speed with which I was able to acquire images between two animals. Now, we use a platform that is heated, so heart rate is going to differ depending on, well, time of day for one. You'll also have anesthetic changes and body temperature changes. So we have the mice rectally probed for their body temperature and regulated their body temperature in a very small window, normally no different than about 0.1 degrees Celsius. And as I demonstrated earlier, the ease of acquisition for the pulmonary trunk images allowed me to acquire images within about 30 seconds to a minute of one another, so the heart rate was statistically identical. One thing that I do want to bring up quickly, this is an image that I took, a short axis view of the left ventricle. This short axis view here, as I hit play, will demonstrate that in some animals following a myocardial infarction, you get non-uniform left ventricular contractions. So if I were to be taking an M-mode image, or even a longitudinal two-dimensional image of the left ventricle, I would be looking at the ventricle from the top to the bottom and would actually see very little contraction and very little ejection of blood volume. And this is because it's actually the septum and possibly the contraction of the right ventricle moving the septum that is ejecting the blood volumes.
Absolutely. So along those lines of validation that you mentioned, pulmonary flow measurements using flow probe or other means of non-ultrasound, like other means of calculation, have you had a chance to look at that? Any comparison with maybe pulmonary flow probe measurement? This is a particular question coming from someone who obviously would like to know any pulmonary flow probe measurements. And so it's non-invasive, if I'm not mistaken. If you can clarify on that question, that will be great, but any comments until then?
Unfortunately, we don't have access to any flow probe machinery, so we were unable to do those correlations ourselves. I was basing my results on Tourneau's study in 2011, where he used a flow probe to correlate cardiac output as collected from a flow probe against the classical left ventricle imaging as well as pulmonary flow. And it was based on his data that I sort of went in with the assumption that pulmonary flow was as reliable as both 2D and M mode for calculating cardiac volumes.
I think, and then along those lines, you mentioned the shape of the left ventricle is distorted. At least in your model, there's kinetic changes here. So obviously, that's going to distort your. If someone wants to use the PSLAX, the long axis view, and then make calculations using perhaps the LV trace tool, their measurements will not be as robust as the pulmonary flow. Am I right to assume that?
Yes, and you're seeing a much lower variability in the, if I go back to this slide, a much lower variability in the acquired data. Okay. And that low variability is what drives statistical significance between two groups. So I don't want to say that pulmonary flow is the be-all to end-all method in just MI mice or just mice following a myocardial infarction. This is really good for any mouse where, say, you even just can't image the left ventricle cleanly and want an alternative method of calculating stroke volume, so you can backtrack to the dimensions in the left ventricle and confirm that you've actually got the right dimensions based on stroke volumes that would be similar between the two groups.
Okay. So if that is the case, then intra and inter-observer variability for pulmonary flow and the area, length, and M-mode techniques. Can you please indicate what those variabilities? I think you mentioned about it in your presentation.
Yeah.
Do you remember which slide it is? Perhaps just to pop it up on screen?
Yeah. Unfortunately, I didn't include the tables of data where I went over the different inter and intra-observer variability. If I can pull up my publication over here.
But would it be available in your publication, your
Yes.
manuscript? Okay, so
Yes.
we should forward it. Please keep in touch with us. This question that came through, we will also provide a link on our Viva newsletter and other communications to you. Please make sure you open your email when we do send you communications through newsletter, so that, especially the person who has asked this question, so that we can provide you with Matt's
with a complete data set for that information.
Yes. Do you have some advice on that note? Do you have some advice to improve surgery for echography, particularly that you have imaged 600 mice in your short career?
Really, the biggest issue when it comes to imaging the left ventricle is anytime there is surgical involvement of the sternum or anything near the chest. So specifically for transverse aortic constriction, you're separating the cartilage from the sternum and the ribs. To be honest, unless you're going to revolutionize the method and possibly go in and clamp the descending aorta, or possibly clamp the abdominal aorta, these scars on the chest are somewhat impossible to avoid. Your best bet is to get very good with your suturing technique so you can line up the cartilage. Again, it's just surgical technique is really what limits scarring.
So Mathew, maybe we should bring you on to show some surgical techniques.
Yeah, the next webinar.
I have quite a number of questions here. Thank you, guys. We're going to take on two more. Was M-mode cardiac output greater than P-derived cardiac output, PSLA cardiac output, as in Thibault's paper? Do you have any speculations on that? Or
was M-mode cardiac
output
pulmonary artery derived versus
PSLA, the long axis?
They found that in all cases, the flow probe actually the pulmonary flow, the PSLA, and the 2D and the M mode all under-evaluated cardiac output as compared to a flow probe. However, they did attribute this to a difficulty in delineating walls using some of the older machines, and between the methods, they correlated incredibly strongly. So it was only in difference to the flow probe where there was an overestimation of the volume using the flow probe. Between the methods, they were very similar.
So if there was there any pressure difference between pulmonary artery and aorta that needed to be factored to flow measurement?
Not that I took into account. The pressure in the pulmonary artery is going to vary by a much smaller degree than it will in the aorta. You have pressures in the aorta that can drop as low in diastole as 60 milliliters of mercury, and in TAC mice as high as 160 to 180, and even upwards of that. Mm-hmm. Whereas the pulmonary artery, we're looking at pressures between about 25 and 45 mils of mercury, and this is why I specifically took my pulmonary trunk areas in diastole. So I was watching the images for contractions and picking my areas at the same point, so I wasn't getting a vessel that was overwhelmingly dilated due to a higher pressure. So I guess that's how I would have controlled for it.
Okay, and so that requires, I know we have had the opportunity to be trained. Andrew Heinmiller, one of our scientific applications, was there last year with you, and with your knowledge, it has brought this study this further along for us to share. Here, a quick question with respect to why did TAC hearts have a similar result as healthy hearts, or appear to have similar results?
Well, this is because following transverse aortic constriction, you get a left ventricle pressure overload. This pressure overload will drive the heart into heart failure, but it won't actually change the wall composition. You may get increases in fibrosis, but generally this is thought to be somewhat uniform throughout the left ventricle. At the same time, you're not getting an abnormal thinning or thickening of the heart in specific sections. It is a uniform increase in left ventricle wall thickness and a uniform decrease in the left ventricle wall contractions. And because that TAC heart still functions under the assumptions that are integral to the left ventricle cardiac outputs from the healthy heart, because you still have that same wall thickness, the same kinetics, the M mode and the 2D derived cardiac volumes still correlate very well with the pulmonary flow.
Right. We were talking about different views. Have you tried the parasternal short axis, particularly at the aortic valve level? Pulmonary trunk is easily scanned and less angled to flow.
To be honest, no, I didn't. Once I started getting very clean, reproducible images from, and I guess this is how my study came up, because you use these very, very advanced machines and suddenly find certain images or certain ways of viewing things that are much easier than you thought, and you're almost surprised that other people haven't used them more often. So no, unfortunately, I did not compare to the short axis view at the aortic level, but that is definitely something that I will look into as soon as I'm back in the lab.
And there was an aesthetics used in your study, correct?
Isoflurane. Isoflurane was used for every single mouse.
And how long were they under ISO? How quick was your imaging?
We're looking at times that ranged from about 15 to 25 minutes, and all the images were analyzed at a post date. I made sure that the mice were not kept anesthetized for too long, as over time, for those of you who do echo, sometimes your images just degrade in quality.
All right, awesome. We've had approximately 20 questions. Mathew, you've handled it very well, and I'm sure there will be questions to come. Please send it our way, and we will be able to communicate with you, Mathew. And I think you are the expert here. You have seen how the study works and shared a wonderful presentation with us. At this point, we are very close to closing and would like to share some updates with you, and for that I will turn the privileges to here. Okay.
Just to quickly answer some questions that I saw pop up. The percent isoflurane, we're using 1.5% isoflurane in 99% oxygen, and the heart rates were around 540 to 570 beats per minute, and the strain of mice used is CD1s, male CD1s, ordered from Charles River Laboratory.
Absolutely. We are going to just check out here. Awesome. Thank you, Mathew, for taking care of that. Our next slide, as we progress towards the end here, will take us to the Stay Connected segment with innovation. As we get the slides up here. All right. So Stay Connected segment, we are going to let you know that we have a way to improve Doppler workflow. What you're looking here is the Vivo 3100 with the pulmonary, with an Doppler image on your top, at the top left-hand corner, and two images onto your right side. And as I pointed out here, I want you to see that. Draw your attention to the image right here. This is the user interface on the 3100, no knobs involved. It allows you for high throughput and presets, customized presets. You can just basically set out the color Doppler view here as shown on the top frame, and basically get your presets ready. All of your presets relevant to color Doppler is set on the side. The bottom here is for that same imaging anatomy. You switch to PW, pulse wave Doppler right here, and all the settings associated with pulse wave Doppler is customized for you here. Some of the improvements we've done to workflow is available on the 3100. Matt, you've had a chance to have a look at it, and I suppose it will be high throughput for you, given that you are imaging 600 mice in your study. So I thought we would share that with you. We will move on to some of our latest news with respect to high throughput and big data, and I would like to bring in Andrew Needles, our Senior Manager of Product Innovations, to actually tell us all about VisualSonics IPACs.
Great, thank you, Mina, and thanks, Matt, for a great presentation today. Just to continue along the vein of high throughput and improved workflow, this is a new software package that we've developed in collaboration with a company called InVicro that is based in Boston. InVicro is an interesting company. They're essentially a CRO, as their name would suggest, but they also offer different imaging and software development services. So in collaboration, we have developed a new module that interfaces with their current IPACs image study management system. So this is a cloud-based system that allows you to streamline your data management, all of your reporting workflows. It allows you to share and collaborate through the cloud across multiple sites and different collaborators that you are working with. So it will take all of the VisualSonics Vivo Lab image data, all of the associated image analysis, many of the measurements that Matt was showing you today, can all be stored, and customized reporting and also presentations can be generated. So it's a very powerful platform, again, all aimed at improving the workflow and trying to streamline that, because we know that many of the researchers out there are working with large numbers of animals, large amounts of data, and large number of measurements. So just a quick announcement on that. If you would like to find out more, please do contact us. There's a news release up on our website, and there will be more updates coming shortly as we do launch this product in the coming weeks.
All right. Thank you, Andrew. That moves us to the latest in cardiovascular imaging. If you'd like to know more, we have compiled a bibliography, publications on different types of pathologies, including MI, more specifically cardiac remodeling, can be found at this bibliography. There's also publications on imaging methods, calculations. I guess we'll have to wait for Matt to publish his to include that in it in this bibliography. Where can you find it? www.visualsonics.com under cardiovascular applications, or just keep contact us on the website, and we will be able to furnish that for you. You'll also see that in the upcoming communications following this webinar. So last but not the least, just like Matt, if you have some expert knowledge that you'd like to share, please lecture on the webinar. All you have to do is contact us at www.visualsonics.com. There's a customer feedback section for you to get in touch with us. Very soon we will launch the Vivo Ambassador program on the website, and you can communicate for an invited lecture on the webinar series. That brings me to the next webinar, March 25th, on vascular imaging, and an April webinar that will follow up on the cardiology aspect, looking at the cardiac wall strain. So March 25th on vascular imaging and cardiac wall strain in April. This brings us to the end of all announcements and the end of this presentation. Mathew, we wish you all the best in your future.
Thank you very much.
And continue to keep correspondence with us, and those who have any questions, good luck in your PhD. And to all those who have attended, thank you very much. This is not possible without this wonderful audience and almost 20 questions. Thanks for engaging, and we will see you soon. Ciao for now.